Today we have an expert on robotics, Scott Walter, a former mechanical and aerospace engineer, to help us understand TeslaBot and talk about why Tesla is leading the way in humanoid robotics. Here's Scott.
Yeah, thank you, Jacob, for inviting me on. Yeah, my background is I think it's close to 4 decades of experience in the area of industrial robots and robot simulation and what we call robot offline programming. So the one problem with industrial robots is while they can do a lot of things, you have to show them how to do those tasks. And that's what's known as robot programming. It's a little bit like, traditional programming is some typing in there, but most of it is actually moving the robot around in space, showing it, I need to go here, you need to go there, once you do this, when you get over there, and all that. And that's always been very tedious to be able to do. And so we've been bringing in tools for the past 40 years to allow people to do that. Let's say we've been using programs to write programs. Sounds very much like AI, right? But it wasn't with AI. It's using traditional structured programming. And now AI is making it possible for us to be able to program these robots even faster, which is why I'm sort of excited about the developments in the AI field and how it's going to impact robots, but also the new form factor. Up till now, robot arms have not looked like the robot arms that we thought of in science fiction. So usually when I tell people that, yeah, I'm working in the field of robotics, they imagine I must be working with C3PO every day. And I was like, no, 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 no. It's like these big clumsy arms that kind of move around, they stay bolted to the ground, and there's a single arm, and it's kind of dumb, and it can bump into things. And if you're lucky, you might have a vision system on it or something like that. But now, if you say you're working in robotics, you could actually be talking about something that looks a lot like C3PO. So we have these humanoid form factors, and it's really exciting how they are going to change the entire landscape, not just of automation, but potentially what labor is going to look like outside of the factory as well as inside the home. So yeah, I'm glad to share my perspective on what's been happening, the developments out there, and hey, what's new? Any video you'd like to talk about today, Jacob?
Oh yeah, I think there is a video that we would like to talk about, and I know you've already been talking about it on Dr. Know-It-All's channel and Tesla Herbert. But if anyone hasn't seen it yet, do you want to quickly give us a breakdown of what's going on here?
Sure, sure. So, what you're seeing is a robot arm, or in this case, a humanoid robot, dual armed robot, folding a t shirt, which may seem like a very mundane task, but it turns out to be a lot harder than you think. So, hard automation is very good at being able to deal with rigid things. Once you start getting things that have a little bit of flexibility or unstructured, they don't behave very well unless you have a really good perception system to be able to figure out what's different about the last time I did this thing. Now, the one thing we have to be careful here is the impression we had is that Optimus was really doing this all by itself. Now, some keen-eyed observers out there noticed very early on that occasionally on the lower right corner, you might see a hand or something like that moving into frame and out of frame. And what that is, it's probably a teleoperator off to the side, which is moving Optimus's arms around using telerobotics to train it in the sequence of doing this. Okay, and that was confirmed a few minutes after this by a comment by Elon saying that this was not fully autonomous, but it should be at some point in the future. So that's the first thing we want to see. It's really Optimus, the mechanism that is folding the shirt with help from a human intelligence as opposed to an artificial intelligence. Eventually, when the artificial intelligence gets blended in there, it should be able to do it fully on its own. What this demonstrates is that it is mechanically possible to do that. Something again that Milan Kovic, who is the head of the TeslaBot team within Tesla, kind of confirmed that what they're doing is they're trying to verify that the hardware is able to do what they want, and then they will proceeding more and more into the software. So this has always been a problem with the robots. Can they mechanically do what you want them to do? And then second, can the software get them to do what you want them to do? And you try to develop both of them at the same time, but if one of them is completely out of sync with the other, then you may not actually be able to accomplish something because of some poor design, some weakness somewhere. And we all know hardware is a lot harder to change than software. Yes, a lot of people will push back and say, are you kidding? Do you know how hard it is to develop software? But the whole idea of software is it's very easy to change kind of overnight. Whereas if you have to change something with hardware, that means your manufacturing process and everything else has to be updated. So if we want to step back a little bit, when I was first observing what was going on with the Tesla humanoid robot project about 2 years ago, I sort of saw that, okay, this is really meant for factory automation. And a lot of people were very excited about the possibilities of what it was going to be able to do. They're imagining it coming in the homes right away. And it was like, whoa, wait a minute, let's not get ahead of our skis. It's designed to solve a particular problem that Tesla has, and that is they want to be able to automate certain parts of the factory that they cannot automate today with traditional automation because it's really designed for a human landscape. And can they come up with something that is able to do the same task that humans need to do? And they are designing it to be able to do that. So if you're working in a factory, there are some things you do not have to be able to do. You do not need to be able to do backflips or parkour in order to be able to work in a factory. Okay, that's not a part of the job requirement. You do not need to be a piano player. So you do not need to have the most dexterous hands in the world. You just need to have hands that are good enough to be able to hold a piece of tooling or a piece of or a part or something like that to be able to move it around. So basically, minimum viable product is what you're kind of looking at. And everyone's wondering, it's like, yeah, but we'll be able to come to my home and fold my laundry. And I said, okay, looking at the mechanism at that time, my feeling was potentially it had the capability to go in and maybe pick up the laundry off the floor, bring it over to the washing machine and put it in there. And without even very sophisticated hands, because if you think about it, just with your four hands, you can pick up a pile of laundry, can't you? And kind of bring it over and dump it in the washing machine. And even with the biggest, bulkiest mittens, you can open up the soap and be able to put that in there. So you don't need to have really dexterous hands to be able to do that. When the cycle is over, you can kind of go in there and grab it again without really super good hands or anything like that, even with gloves or without them. Take them out, put it in the dryer, get the dryer to turn on, and take it out, dump it on your bed, and maybe sort them out into different piles. And you can imagine a perception system that should be able to sort files by either type or color or something like that, be able to do that. And then it was like, yeah, but can it fold it? And I'm just like, I'm not sure because I've seen a lot of people trying to work with industrial robots in fabric, and it doesn't work out well. And one person who knows that is Elon, because when they tried to automate the Model 3 line, they were putting in what was kind of a flexible component that's supposed to be some insulation underneath that was not a very rigid part, and they could not get the automation to work. And that was why Elon was sleeping on the floor. They were trying to figure out how to do that until eventually he found out they didn't need the part in the first place. And it was like, but still, it was one of these things that they learned the hard way that industrial automation is really good with rigid things that are in the right place. But when you start having flexibility in there, it becomes a bit harder to manage that and sometimes almost impossible to get done. So now you're looking in there, and my question is like, okay, can Optimus fold something like this? Well, we had an idea almost a year ago, and it didn't come from the Optimus team. It came from some graduate students in Stanford who started playing around with some telerobotics in which they had these hands, which were probably, I would call, the crappiest hands possible. They were just these two parallel grippers that kind of came down, just these pincers. And with it, they were doing amazing things. They were like opening up a jar. It's like, wow, that was amazing. They were opening and closing Ziploc bags. They were even taking a zipper and putting in there, moving along. And now think about it. With our hands, which are really good, we find it a challenge sometimes to be able to do a zipper. Now, this is something they were doing telerobotically. So the intelligence was, again, human intelligence figuring out, but they showed that mechanically you could have something that seemed pretty bad and you could get it done. Now, it doesn't mean it was the easiest job in the world. It was still very difficult for them to be able to do this. Yet, they showed that you do not need it's the problem is not necessarily the hardware, it's all in the software, in the intelligence of the system that's driving it. It's able to compensate for the fact that the mechanics may not be that good. So it's like Optimus probably can do that. And then again, the Aloha project, which came out just after New Year's, it was like, the first thing that hit 2024 that everyone was talking about. Again, these same grad students at Stanford that now taken that same platform and made it mobile had gone around and shown cooking and cleaning, and then later on showing that they could telerobotically go into the apartment and actually do the laundry and fold some shirts and do a few other things. In some cases, they did it autonomously. They were able to show that with enough training cycles, you could teach some sort of large language model or through machine learning a way to be able to autonomously do these tasks with about 80 to 90% success rate. So that's rather amazing that you could have that small of a training set. So what Tesla is doing here is they're trying to get the training set to be able to train Optimus to do this. But the other most important thing is, it's like, I think we knew the answer to the question, but just because you think you know the answer to the question, you've got to demonstrate it. Is that Optimus mechanically has the capability to be able to fold a shirt? Now, I know that's a really long answer to what is a very simple question. What are we seeing here? What we're seeing here is the hardware is ready to do these tasks. And Milan's tweet more or less came in there and confirmed that yes, they're satisfied with the hardware. And now that means they can start pushing ahead more and more in the training sets for this hardware. But more importantly, if they like the hardware, it means they can start building more copies of Optimus. Because if it turns out
Mm,
there's like some major deficits in the hardware, you don't want to suddenly build 1,000 of them and say, oh, guess what? There's a problem with the arm, and we have to make all these modifications. They want to validate that first, and the way you validate it is you stick in a really smart system to drive it. That smart system doesn't exist yet. Well, yes, it does. It exists in the form of a human being. So a human can go over and show that. And that's what's going on here. So that's the importance of it. Now, of course, a lot of people thought it was Optimus doing it completely by itself. Not yet. That's the video we're going to be waiting for maybe in a couple of weeks, where they show the exact same thing, but in this case, fully autonomously, with it being unstructured, with a bunch of t-shirts all over the place, and seeing Optimus actually be able to grab them, bring them over to the table, and do the folding. That's what I'm waiting for next.
Elon said in his tweet that it can only do it right now with one shirt in the box. If this is
Yes.
teleoperated, why does it matter that there's only one shirt in the box if it's being teleoperated?
Oh, it should be able to do multiple ones. So that is, I guess, a little bit interesting to say. Well, yeah, I mean, if a human is over there, a human should be able to do it. It would only make sense is because the teleoperation is like really hard to do. You might be struggling with it a little bit, but I would think there's no reason why they couldn't put more in there, or at least they're training it with that, with the expectation that they would be able to see it autonomously being able to do it. Eventually, it should be able to be completely unstructured, that the shirt will be anywhere. You would be able to say it, find all the shirts within this particular area, and maybe find them all with a particular color, and now bring them up here and please fold them, and then go ahead and go through that process. And then it should be able to understand, what it's basically labeling and understanding different objects, what they are. It's going to know that, oh, the basket is a basket and the t-shirt is a t-shirt. They're clearly different things. I know what I need to fold. I know that I have a table that is appropriate for doing it. The height of the table shouldn't matter, the position of the table or location, none of that should matter. It should just be able to adapt to that and be able to do it. And that's what we'd be looking at next, is that it's working in a truly unstructured environment. And again, it's a question of how many training sets they need to have. Now, teleoperation can be a bit trickier than it looks. And I'm really impressed with the team from Stanford and what they were able to do with a telerobot they have, because they're basically using kind of a telerobot operation by wire kind of mechanism, where you have one arm that you're able to move around, and the movements of that arm is then mimicked by these other arms that are actually doing the task. So they're moving those things around. The thing is, I'm not sure how much haptic feedback they get from that. So if the other arm that they're moving suddenly runs into resistance, whether the arm that they're driving suddenly stops or gives them the feeling of that resistance. And that's something that is very important to, especially when you go to grab something. If I'm going to pick up an object and I have some sort of manipulator that allows me to close down like this, and it causes the other fingers to kind of move with it. And if one of those fingers suddenly hits resistance and I'm able to kind of do this, that's kind of unnatural and doesn't feel right. I would need to get an idea of what I'm feeling. And all telerobots actually were driven by cable. They had these cable mechanisms, so that as you were moving the master arm, the follower arm, if it hit something, you would feel that, and it would kind of come through, and you'd notice there's some resistance. If you go to grab something, you get a sense of that feeling. And when you're using the controllers that they have, which look like data gloves, you get some haptic feedback, but that's more or less in the sense of like vibration, not necessarily telling you how hard or soft the object is you're attempting to pick up. So a lot of that has to come from what you're seeing visually. And I'm assuming the teleoperator, because you see the teleoperator's off to the side there, he does not have the same field of view of Optimus. Or does he? He's probably wearing some goggles right now, and he's seeing the world through the eyes of Optimus at this point, even though he's not right there. So he's looking at that and picking up these objects, and he's got to get a feeling that if I close my hand down, have I actually gripped it right? You may think you gripped it and you go to pick it up and suddenly the shirt's not there. So you have to do that visually. You need a really good visual feedback to be able to tell. And now there are sensors in the tips of Optimus right now, and those sensors might be helping them, the operator, get a sense of a feeling. It's like, oh yeah, look at this. You definitely have contact, and it seems like if you get strong contact, you can go ahead and move ahead. and do this. And this is going to be very important. And that was also a question of whether Optimus was going to need some sort of tactile feedback. So the impression I always had is that, all right, the minimum that you have, and again, is that we know how to move our hands in space. So I'm going to ask you right now to touch your nose with your fingertips. So you should be able to do that, right? Is that fairly easy to do? Just go ahead and do
Yeah.
that. Now, if I ask you to close your eyes, can you do it again? How close do you get?
Do you want me to touch it or try to get
Yeah, just go
close?
ahead. Go ahead. Go ahead and touch your nose. See how close. See if you touch your nose with your eyes closed. I'm going to do mine. Now take your head and like turn it to the left or to the right, and again try to touch your nose. You come pretty close to it. Now pivot your
But you
head
don't.
anywhere randomly in space, and then move your fingers around and see, can you touch the tip of your nose without seeing? And you come pretty close. And if you practice enough, you might be really good at that. I can even, I can take both hands and I can move this hand around here, and I can take this hand here and come over here and come pretty close to touching the thumb in this hand. Now I'm going to want to touch the center of my palm. I kind of know where they are, and I'm able to do that because of this concept of proprioception. This idea that I have a mental model in my head that I know where everything is, and I know what I have to do to move my fingers to where they need to be. And that's what a robot has as well. It has this built-in model. It's usually called a forward kinematic model that says, if you need to go to some Cartesian location in space, these are the joint angles we need to calculate for you to get there. That's actually the inverse kinematics. The forward kinematics is like, if this is what my joint angles are, I know the Cartesian location that something is in space of my fingertip right now. And if I know I have to get to my mouse, which is over at some other Cartesian location in space, I can see the error between where my tip is and where that is and figure out how to move down there. Now, one of those I can kind of do it with my eyes closed and maybe guess where it's going to be. And I might get close but miss it. But once I turn my eyes on, my eyes are then able to go in and be able to mid-course correct to make sure I get there. So in order for any sort of humanoid bot to be able to do these things, if you've got a strong perception system and a pretty good idea of what the model looks like of the arms, you can get really close to where you need to be without actually having to have the tactile feedback. So that's one thing that will allow you to get there. It doesn't hurt to have the tactile feedback because sometimes when we go to grab something, it's a little bit out of view, isn't it? It's like, something behind my PC here. I've got to get some connector in here and I can't quite see it, but I can feel the connector and everything else, and I might want to play with that. That comes in handy. That's really nice to have, but it's not necessary so long as everything is within your field of view. But there's other things that perception can do. And certainly with the robots, even though they don't have any tactile sensors in them, they do have feedback from the motors. So when the fingers move without resistance, it only requires a certain amount of current. But as soon as it comes into some resistance, the current spikes a little bit, and that can be a signal that's interpreted by the controller to say, hey, we've just hit something. That's information. That's telling you. And I'm going to attempt to push a little bit harder. And then again, by continuing to look at that current, you can see, is that thing I'm grabbing something squishy or something hard? So they already have some built-in tactile feedback, even without tactile feedback. So that's already there. And then when they add it in the tips, they get a little bit more. Now, there's one other thing that we do is if I put a couple of objects in front of you, Jacob, let's say I put a baseball, I put a rock, I put an egg, and I put a Nerf ball, and I ask you to grab each one of them. Before you even grab each one of them, you already have a mental model in your head on how much clenching force you're going to need to pick up one of those objects. Let's say you put a shot put there as well, because we know a shot put is really pretty heavy, and it's got a kind of, let's say, slippery surface on it. So you already know when you go over the expectation of what your grip strength is going to have to be before you even get there. So if we look at an egg and we look at kind of a baseball, you know when you go to pick up that egg, are you going to be delicate when you pick up that egg?
Yeah.
Yes, you already know from the School of Hard Knocks that you don't grab that the same way you grab a baseball. And then when you go to grab a Nerf ball, you know when you grab the Nerf ball that it's okay to apply a little bit more force to get it to deform. So that's a priori information we have before we grab an object. This is the same thing that artificial intelligence is going to be using as well. So when Optimus is looking at these different objects, when it sees an egg, it's going to know, whoa, that's an egg. I have to grab that very differently than I would grab a baseball, which is a similar size object and maybe similar in weight. or maybe a golf ball. Let's say something like that might be about similar. So, and you know, kind of from experience that some objects um, are let's say very rough. So when you grab them, they don't slip out of your hands that easily. And others, you need to like grab them in a particular way. And some you might know you just can't grab them at all. They're too delicate. Like if you had a glass sphere, you might say, "Oh, I'm grabbing that thing from underneath because I don't want to be putting a lot of pressure on it this way because it might implode." So this is all a priori information you're going to use. That you identify the object, and then from that you're going to come up with a completely different strategy on how you grab it and what the force is going to have to be when you start to come down on it. And if the let's say the expected force that you are generating and what you're getting back differs, then that tells you, I made some wrong assumption about this thing. So it could be that you're looking at something that looks like a Nerf ball, but it's actually very, very hard. And you're expecting it to be mushy, and whoa, wait a minute, it's not. So and then you're going to have to adjust. But for the most part, they're going to be able to make a pretty good guess of what's going on because we do that already. We simulate in our head what we expect the task to look like, whether it's doing something in the house or if it's driving the car. So when you're driving the car, you're already thinking 10 seconds ahead. You know where you want to drive. You're thinking what the next maneuver is. You're looking at the curve and everything else. So again, a perception system which is just based on vision can be a lot more powerful than you realize because you're not only seeing where you are in the world, but you're identifying those objects and telling something about what's the expectation that you're going to be getting from that particular object when you go to grab it. What is the best strategy? What strategy has worked in the past? And if it's something new, that's where you need to start thinking about curiosity. You need to say, I haven't seen this object before. Let me experiment with it. Let me pick it up a few times, different ways, find out which way works. So again, long explanation. I'll let you pop in a couple of questions.
Yeah, long that was great though, and I love what you do with your hands. It really helps us immerse. But have you seen Ready Player One?
Yes, yes.
Direct. Yeah, so when you're talking about teleoperation, it got me thinking about Ready Player One and how they put on their headset and they go into this alternate universe where they control things with their body. And now that we've seen
Mm-hmm.
teleoperation when folding laundry, it got me thinking about, the possibility of maybe Tesla hiring. I mean, Tesla probably wouldn't do this because, that what they're doing with neural nets, they want these bots to be autonomous. But you could have other companies try to leverage teleoperation to hire cheap labor in developing countries. And maybe these people put on a headset like this guy's doing with Optimus here, and they do a work in a factory from a remote location. Have you thought about this?
There's a potential for that, and it could be a big potential if you want to have, let's say, a low-cost workforce to be able to do a lot of the training. But once everything gets trained, they should be able to do it autonomously. But there could be certain situations which is very novel, very new, where you do want something very remote. Someone be able to operate something because it's an emergency situation, some sort of crisis situation. But there are some ideas that potentially could do that. The one thing that I think Tesla is a little bit concerned with is that when you kind of open up for remote operation, it means bad actors can come in and do something. So I think they want to kind of keep their ecosystem as closed as possible and kind of air gapped from anything else if possible. The other thing about Ready Player One is that virtual reality has been great. It's a wonderful experience you can go into. So when you immerse yourself in there and you have a data glove and something like that, and if you hit a wall, you get some sort of haptic feedback, but it's not that your hand suddenly stops or your hand hurts. You might get some vibrations say, hey, you're hitting the wall, move your hand away. So that's not really a natural feeling, but it's some sort of feedback because that's the best we can do because we don't have the real holodeck experience right now. Now, of course, the reality is if you're in your house, you might walk into the real wall, in the virtual world, it's not there. So sometimes you want to have the two to match. What Ready Player One was trying to do was figure out how to come up with that suit that gave you the full feedback, right down to remember the guy getting kicked in the nuts and it really really hurting on the suit. So that you don't have something like that. That would be the great thing to be able to have something like that. That as you hit something really hard, your hand will actually physically stop. So right now they may be using a simple data glove and something as simple as like Connect. So just or something that they built themselves, but potentially you could be doing teleoperation using a system as simple as that, because all you're doing is you're tracking the location of the hand in space, and with that, using it to tell the Optimus robot how much to move. And it's sort of like the mouse on your screen. If you think about it, the cursor on your screen is completely disembodied from this mouse. Yet somehow we're able to map the motions of our mouse with what we're seeing up there. So even though there's not maybe perfect movement, all I know is like, oh, my hand is here right now, and Optimus is like an inch off from where I need to be to the right. So I just need to move my hand a little bit to the right, and oh, I can see the Optimus hand is going to move to the right as well. So there will be a very close matching to what's going on with the user or the teleoperator, but let's say it won't be down to necessarily the millimeter precision. It doesn't have to be. All that matters is that what you see is the desired effect that you want to have to be able to do that movement.
Okay, and you said that Tesla's hardware is now ready to go. We're fired up. Now it's time to move on
Mm-hmm.
to getting the software ready and the AI training. So we've seen, correct me if I'm wrong, two types of training for them to get their data. The one with the camera on the forehead and the guy's doing the task himself, and now
Yes.
teleoperation. So does teleoperation basically help them get the proprioception better, more so than the
Yes.
camera on the head? Okay,
Yeah,
got
well,
that.
I think you're using different sets. So the camera those they had, the impression I had when they were doing that is they were training what looked like a simulation version of Optimus. So they were getting all that data and probably using that to do a little bit of
Oh.
machine learning on that. So they didn't necessarily have to have the physical Optimus, but they were going around and moving that. And then they were able to get the end-to-end to work with the Gen 1. So the blocks that were moving around that we saw in September, that was end-to-end, fully autonomous. They were able to do that. That's something that Milan pointed out, said, hey, we did this in September with the other one. This is something new that we're doing where we're using a lot of teleoperation right now in the real world. Because when you are working in a virtual world, your physics is good but not perfect. And the real world physics is a lot messier. So a lot of times, like folding a shirt, that is really hard to simulate, okay? Simulating boxes or blocks being picked up and moved around in the virtual world, that's easy. But being able to get this thing down is a lot harder, which is why you have to start doing some of these things in the real world and why they're bringing it into the real world right now to get that set. So they're using multiple inputs of training data. And we don't know if they're going to take a similar approach of what Figure did, where with the famous coffee cup and putting the pod into the coffee maker and making the coffee, that was done just through observing humans doing it. Not quite sure what that means, whether that meant they were just videotaping that, whether the humans were wearing a GoPro, and so that that meant you get the point of view of the human and what it was like to put it in there, and then they used that to do some sort of machine learning, and then the bot was able to kind of replicate that. Or was it the bot actually observing the behavior? Because if it was literally the bot sitting there watching people doing that, and after so many hours of observing that and then training on that, being able to do it, that is very, very impressive end to end. And that's what we would like to see eventually, is that
And
you bring it up. Mm-hmm.
And they said it was 10 hours of training, if because I know you said there are
Yes.
hours, and
And it
I
wasn't
just want
clear whether that was 10 hours of like observing or whether that was 10 hours of actually compute. So, I mean, no one is quite sure. We hope to be able to kind of get an answer from Brett on that exactly what that is. But still, it's impressive, whatever it was, 10 hours to be able to teach a task like that. And if it really comes down to that, you can set up the bot that the bot will come into an environment and observe people doing something and you have a little bit of banter with it. So I'm sure if that's the way it was, I imagine they would have kept on saying, "Hey, Figure, I'm making coffee. Hey, look at me, Figure, I'm making coffee." So they would say that again and again, and then you would associate the action you're seeing there with some sort of vocabulary or language, so that as you notice, they went up there and said, "Hey, Figure One, make me a cup of coffee." It knew, oh yes, I've seen humans do this before, and I know how to do this. It'd be that, and so I imagine they're all trying to do the same thing, but we don't have enough details on that. It's very impressive what they did. We just don't know enough details to know whether it was like very similar to what Google already did, the DeepMind group back in the springtime with RT2, where they had also used video training sets to be able to train their bot to be able to do a variety of tasks. And you may remember that particular one where they again used like a large language model to ask it to do something it had not been specifically trained on. And one of them was that they had pictures of flags on a table, and they said, move the banana to Germany, and it knew to take the banana and pick it up and move it over to the German flag, and a few examples like that, very similar to what Agility was able to do in their example with picking up the box. off of one stand and bring it over to another using a large language model, where their description was, let's say, not very direct. It was like, pick up the box that's the color of Darth Vader's sword and bring it over to the tallest tower. And it's like, wow, that's really vague, you know. But why don't you just say the red box, explicitly like that, and bring it over to number 4? But that meant it had to go through and observe things about its world, understand characteristics of the world, and be able to do that through a large language model. So again, that's a very impressive way of being able to interact with these bots, and what we're going to be seeing more and more of in the future.
Amazing. And as we try to get to the next step here in terms of the conversation and wrapping it up, we're talking about all these other startups and progressions in humanoid robots. How do you see this market evolving, and what kind of advantages do you think that Tesla has that you could call moats?
Okay, so they it's a huge TAM. I mean, it's so big. There's plenty of room for everyone to go in there, and but there certainly could be, if someone comes out with a killer app really early, and is way ahead of everyone else, they could end up getting the lion's share of that entire TAM. The moat that Tesla has, I think, is this: is one, is they are their own user. So for a lot of the others, they need external users. They need customers, and they need customers right away. So in many cases, if you're in a perpetual startup mode, you're constantly waiting for more rounds of funding and everything else, and the venture capitalists start getting a bit impatient after a while. It's like, when are you going to have a product that's ready to go? Tesla does not have to have the perfect product to be able to start using it. Some of the others, like Figures, it seems like they may have some corporate groups that they're working with that are, let's say, very patient and eager to test this thing out, to give them the kind of the feedback. So they may have something like that. But from the Tesla standpoint, they do not have to have a product that's ready to release. All they need is something that is good enough to start using internally, that starts doing useful work in the factory. And when it starts doing useful work in the factory, that means it is actually adding value to the product and is helping to reduce the cost of goods. So that means the margins will go up. So Tesla doesn't make money by selling the Tesla bot. They make money by the fact that it drives the cost of their goods down, and they can sell them for a higher margin. And that is, the kind of the flywheel that they would have, and it allows them to experiment and experiment and experiment. And then when that gets good enough, they can start to go down their supply chain and start moving out to their supply chain. And trust me, once it gets out the supply chain and starts working, a lot of the other OEMs are going to take notice, and they're going to either look around who else has got something as this capable, or they're going to come to Tesla and ask them, can you go ahead and start selling these things to us? The other thing, I think, huge moat that Tesla has is that they are already experts in manufacturing. And part of being an expert in manufacturing is this principle called design for manufacture. And they designed the Optimus robot right from the beginning to be easy to manufacture. They said that again and again and again, and they keep on talking about their selection of materials to keep costs down. They do not want to sell this for $100,000. They want to be able to sell it for less than the cost of a Model 3. That's already been said. And I suspect they could easily sell it between $10,000 and $20,000 if they sell it. More than likely, they're going to use it as a leasing type of model, or what you call is like robot as a service, for a while, because the actual value of the bot to a manufacturer is in excess of $100,000 a year easily when it's fully capable. So now they would be able to produce it for a lot less than everyone else. And most of the other bot manufacturers out there, they are not manufacturers at their heart. So they may find scaling up to be very difficult and the cost to be very, very high. So it may take them a while to be able to get down into that area. The other huge advantage that Tesla has is that they've been working in full self-driving for a long, long time. And that's the same AI technology that they're using inside of the bot, because they realize, hey, it should be an easy pivot from what we're doing over here for making the cars full self-driving to also be able to do it for a humanoid form. They also know a lot about actuators. It turns out there's more actuators in like the Model S than there are in in the Model X as there are in Optimus. Different kinds of actuators, of course, but still, they know a lot about actuator design. They know a lot about having them produced and being able to produce them at a reasonable cost. So I think one of the big things for them in the end is going to be the manufacturability and the fact that they'll be able to scale faster than anyone else.
And before we end, if you want to quickly talk about what they said at AI Day about designing the actuators for Optimus and
Mhm.
how many tests they were doing and how they were trying to find ways to make just one design of an actuator work in different limbs of Optimus. If you want to talk about that quickly before we wrap.
Yes. Yes. Now, the Gen 2 design of Optimus has 42 actuators in it, total. That's a total number. However, there's really only 7 different types of actuators. There's the actuators in the fingers, that's one, and then they have 3 linear drives and 3 rotary drives for the limbs, the torso, and the head, and everything else. And when they were looking at the actuators, they could not find any on the market that met their requirements explicitly. And it didn't matter the cost. I mean, it didn't matter how much money you were willing to spend. Obviously, they want them to be very as cheap as possible, but they were looking at them to be very light, to have a certain amount of power, certain characteristics as far as energy consumption, because you want to make sure the bot can operate for 8 hours. So they looked at it and said, none of them out there can meet our specs. They're not the only ones. Brett Adcock from Figure has also said they had to design their own. And I suspect some of the other humanoid robot companies out there have done the same thing. It kind of looks that way, even though they haven't come out and said that. I'm not sure if agility has taken them from off the shelf or whether they're building them themselves as well. I suspect they may also be designing their own. And part of it is because no one's been building these things before, so you don't expect to find them in the catalog. Now, you could look at the bot, cut it in half. Okay, so you get 42, but in the end, it's almost like you have 21 unique actuators that you would have to have from all these different places. But it turns out in many places that the torque requirements and the power requirements are nearly the same. So close, it's like, do we really need to have a unique actuator for that? Maybe we can use the same actuator for it. And they wanted to get it down to being a very small family of actuators to have a much smaller number. So they really have only 7 in total. And so, for instance, up in the shoulder, there are 3 actuators in the shoulder. They are the exact same 3 actuators. So 3 of them are right there. It turns out that the actuator that's up in the shoulder is also used down in the hip. There's 2 actuators down on for each leg, and also for the torso itself. So that same actuator that appears up here 3 times and over here 3 times appears down in the torso 3 times. So it's used basically in 9 places, that one same actuator. So when you think about it from if you reduce the number of parts that you have, the number of parts used, it makes it a lot easier to manufacture, keeps your cost down. You get a certain amount of replaceability in there. And then if you go along there, just about every single actuator is used in more than one place. But one of them that was kind of curious was the arm right here, where the arm is able to do this roll. That actuator only appeared there on the left hand and the right hand. So it only appeared in 2 places. And that was kind of curious to me. Say, why did they go to the expense of coming up with a specifically designed actuator for that? And the reason is, I think, I've been able to prove it, the Gen 1 had no neck movement. Gen 2 now has neck movement. The actuator that's here is the lightest of the rotary actuators. The other 2 actuators are much bigger than it. The head does not have a whole lot of mass. Not like you don't need to walk with your head or do anything like that. So I suspect the actuator that's down here is up here. So you have two more of them up there. That would make sense on where they're going to go. I don't think they designed anything special for the neck. I think they were using that. And if you ever go to the Tesla store, in some places they actually have the Gen 1 robot mannequin. I call it the Opticon, sitting there in the showroom for you to look at. And you can go up and you can look at it, and you'll see the motor that's there. You'll see there's all these things kind of sticking out from it, and you're like, what are they there for? And a lot of the reasons why these things are there is because they're taking these motors and combining them in different locations. They need to make sure they're able to match up in the different locations it's supposed to be. So even though a particular hole may not be needed for where that location is, it's needed somewhere else. And I suspect they designed it already with the idea of going in the neck, and they decided to not use the neck in the Gen 1 to see if they get away with it. And they decided, we do need the neck movement after all, and they went ahead and put it in. So if you ever can get near a Tesla store, I would recommend you just go out there and take a look at what's going on.
Appreciate it, Scott, and thank you so much for coming on today and sharing your intel with us. In 30 seconds or less, what do you expect to see next in the from Tesla and the humanoid?
30 seconds. You're only giving me 30
That's
seconds.
it.
Well, I will try my best. So what I think we will see is that we're going to see some more autonomy here. This particular action being done fully autonomously without Telerobotics, just to be able to prove they could do it. The other thing I would like to see them do is walk up steps. No one's really shown them walking upstairs. Everyone's shown their bots can walk, but no one's shown that their bots can go upstairs yet. I would like to see that.
No, I wish I gave you more time. That's fascinating.
Aha. There's lots of things, and the other, of course, is to do to see it doing a real task on the factory floor. That's what everyone wants to see. Is it already
Yeah.
working in the factory? It could be. I'm sure they're testing it out there yet, but they haven't shown us that. Instead, they're just showing us that it can fold a T-shirt.
Yeah, and with Alexandra's notes, she noted on the jobs Tesla's been posting, it's pretty crazy. They're talking about a machine to build a machine, talking about hiring people to manage 1,000 bots at once. I mean, this thing's coming faster, and you've been in the space a long time, and I can't stop asking you questions because it's like a luxury to have you on my channel. But has things moved faster than you would have ever expected?
Oh, very, 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 very quickly. It was very impressive to see how they went from announcing the project to, in less than a year, having something that was walking. A walking bot is very challenging. It's very difficult to do. Yes, there's been a convergence of a lot of technology and control system theory and everything else, and engineers are being taught a lot of this stuff. But still, if you read Walter Isaacson's book about the beginning of the Optimus project, it was like, oh my God, they don't know what they're doing. They just like threw a bunch of people together that are smart people but have never worked in this space. And I'm like, my goodness, this is a recipe for disaster. Turn out it's not a recipe for disaster. If you bring in people who are, quote, all the experts in that particular area and been working in the field of robotics for a lot of time, especially humanoid robots, they will be fighting over the design for such a long time, you won't produce anything because they're all trying to perfect it. This guy thinks he has the best hand design. They got to go with hand design. Other people are saying, no, that's not what we want to have. So I'm going to go. They didn't know anything. They figured it out. They did their research and bam, they get everything together quickly. So I think they've got the perfect team that knows how to be lean and mean and to make progress really fast and not be afraid of what they call fail fast, because that's the only way you make progress. You do something, and if it fails, well, we know that's the wrong approach. Let's move on to the next, to the next, to the next. So yes, they've gone very far very quickly. I can't believe it's like maybe 2.5 years since AI Day One, maybe a year and a half since they really displayed the very first Tesla bot. So this is remarkable progress. And the thing you can see, there are other companies doing the same thing also really quickly compared to how long it took um, Honda with Osmo to be able to get it to actually walk and do things, as well as Boston Dynamics. I mean, they'd been around for decades working on these problems, and suddenly whoosh, these people come up in startup mode and come out with it pretty quickly. So it's going to be moving fast, and it's been the convergence of the technology. The mechanics, we could have always come up with the mechanics. Yeah, little things with the control systems here or there that have made things a little bit easier to do with slightly faster computing. But what's been missing is the brain. And with the advances in AI, that's the convergence. That's the final piece that actually makes the dream of a humanoid robot possible.
Yeah, and Elon says it's harder to get GPUs right now than it is to get drugs. So that seems to be,
Oh, I could believe it. I could believe it.
yeah.
Yeah, yeah. It probably is. And if you want to think about it, it's like, mechanically, we've been able to come up with things that are almost convincingly human for the longest time. Going back to the 19th century, there were these things called automatons, which basically clockmakers figured out how to come together and make them move around and look like, they really are human. And if you want to see a bot that's almost convincing human, just go to Disney World. You'll see it all the time on the Pirates of the Caribbean tour. It's like they're there, they move around, they're kind of able to do it. They can't walk, and a lot of them are like right in place. But at the same time, being able to get that movement has never been a problem. Being able to program it has been a bit of a challenge to get it exactly the way you want, and then to give it the intelligence to actually do something that's different than whatever is this scripted motion. That's something else. So the mechanics is always something we've been able to do. It's just we've been missing the AI.
Yeah. Well, I look forward to seeing the progress over the next couple of months. And thank you so much for coming on today, Scott. Everyone, make sure you are following this guy on Twitter. It's Going Ballistic 5 is your handle. Is that correct?
That's correct. Yes, we'll find out there. And again, thank you very much for inviting me on, Jacob. And hopefully, I was able to inform everyone a little bit about what's going on and what to expect from the future.
All right. Thanks, guys.